Thank you so much.
Okay, so we have Irfan Bagci from the University of North Georgia. He'll talk today about Whittaker modules for Cartan-type Lie superalgebras.
Thank you so much for the introduction. So I'm happy to be here to see everybody in algebra group. So I'll talk about Whittaker modules for Cartan-type Lie superalgebras. I have this result for a long time, but I never had a chance to type them. Finally, I typed them, and thank you for inviting me to give a talk, and I'm happy to be here to talk about these results. So I have some other results for other types, but I just want to focus on Cartan-type Lie superalgebras. Okay. Okay, good. I have to click the screen first. So let me give you a brief history of Whittaker modules first. So I will just focus on history of Whittaker modules and work on Whittaker modules for Lie algebras and Lie superalgebras. There are lots of Lie algebras. There are lots of algebras, some kind of Lie algebras, which have Whittaker module defined for them, but I will not talk about them. I will just talk about in the case of simple Lie algebras and semi-simple Lie algebras case, and Lie superalgebra case. I'm skipping lots of history, just semi-simple Lie algebra case and Lie superalgebra case. Okay, so if you want to define Whittaker modules, we need to have a triangle decomposition. So that if you take a semi-simple Lie algebra with triangle decomposition, then you can define the notion of Whittaker module. So we take a Lie algebra homomorphism from N to C from the important part. And then a G module, if you take a G module V, then we can talk about Whittaker vectors. A Whittaker vector is a vector in V such that the N acts by psi, by scalar by psi. For every X in N, X times the vector should be psi X times the vector for all X in N. Now, what's a Whittaker module? A Whittaker module is a cyclic module generated by a Whittaker vector. So it's basically U of G times W for some Whittaker vector. Let me say this: these are non-weight modules. You can see from the definition because psi may not be zero, may not be. It's a non-zero linear function. We see these modules in the work of first I see in the case of Lie algebras, in the work of Arnold and Pinks in 1974. Such modules first time I see in this paper. And after this, the main work is done by Cartan in 1978. He proves many results for semi-simple Lie algebras in his paper. Among his important results, one of them is he gives a complete description of simple Whittaker modules for semi-simple Lie algebras. He basically shows that if you fix for psi, then simple Whittaker modules for semi-simple Lie algebras, they are parameterized by central characters, uptime geometry. That's what he proves.
I know Cartan had a paper, but I've never actually understood what is this? Like, what made people, if you happen to know, like, what made people start to think about Whittaker modules? Because from somebody who thinks about weight modules, this is kind of the opposite of that in a sense. So not the opposite, but so what motivated? Do you happen to know, like, what motivated this definition?
I think it comes from number theory. They're called something called Whittaker equations. That's what I heard. It's related to Whittaker equations in number theory. I don't know much about these equations, but that's where they show up. The name comes from them. And then and you see this module, they look at all kinds of simple modules for the algebra, especially in the work of Block. You will see for SL2, there are two types of simple modules. Highest weight modules, Whittaker modules. There is one more type, I don't remember the name. Some kind of localized modules. So Whittaker module is one of the simple types of simple modules you see for the Lie algebras. They are infinite dimensional and they are non-weight modules.
So, like for the SL2 case, that's the only case that's known where they can classify all the simple.
Yes, that's all. Again, I said the block shows like for SL2, there are three types of simple modules, any kind. So Whittaker module is one of the types, and they are always infinite dimensional. We see the Whittaker module in the work of McDowell in 1985. He does some nice constructions of induced modules from Levy subalgebras. And they get some nice results. And then this work is generalized by Miligit and Sorgelak in 1995. I basically follow their work for the superalgebras. The work of Cartan, McDowell and Milicic. All right, so, and then with Emily and Konstantina, we defined look at Whittaker modules for these superalgebras. They know Whittaker modules, and I was working on these superalgebras. So we decided to look at Whittaker categories and Whittaker modules for these superalgebras. And we have a paper on this. So, and then, yes,
One question. So, when we, inside zero, we have like highest main modules, there's like this whole kind of
yes.
category O story. How parallel is this story to that? Like, should I have that in mind, or is it just a totally?
Yes, there's a category of Whittaker category, same almost same notion. The Whittaker category is a category of G modules, which are locally finitely semi-simple as N. Basically.
And is this like the highest weight category, that type of stuff, or is it like a different thing?
Different, I think. I think yeah, it's different. I think we give a decomposition of this category in terms of blocks in the first paper. Yes. Did I answer for your question?
Yeah.
Okay. Okay, so I am not sure if everybody, I mean, I will just give definition of Lie superalgebra. I don't know why, all of my talks. First part, I try to make it very easy. A Lie superalgebra is like super version of Z2 the version of the algebras. It's a direct sum of two vector spaces, even part and odd part. So the vectors in the first part, the even part called even, the odd part called the odd vectors. And then to be a superalgebra, you have to preserve Z2 grading. First of all, and then you have the graded versions of anti-commutativity and what Jacobi identity. And if you restrict the definition to the even part, you basically recover the definition of the algebra. So the even part is always a Lie algebra. So every Lie algebra is a Lie superalgebra, which has odd part being zero. Of course, like we define definition for homogeneous elements and then linearly extend this definition to all of it. Okay, so we have superversion of everything. So we have general linearly algebra, we have general linearly superalgebra. You take space of m plus n by m plus n matrices and you decompose it as a direct sum of two vector spaces, even part and odd part, basically. And the bracket is a superversion of commutative bracket. So xy minus yx. Here x bar and y bar denotes the degree of homogeneous elements. It's either 0 or 1. If x and y are odd, then middle sign becomes plus always. Otherwise, it's usually commutative bracket. If x and y are odd, then you get xy plus yx, the bracket. Otherwise, it's xy minus yx. So, same bracket, all the same bracket. Okay, so if you look at the representative of Lie superalgebras, you see a difference. When you look at the important Lie superalgebras, you use representations for a finite dimension. Important Lie superalgebra may not be one dimension. This creates a problem when you try to extend the results of constant and other people to super case. You cannot directly do the same thing. So the modules for n may not be finite, may not be one dimensional. That's the reason. This creates a problem the way to use the constructions. Okay. And the classification of, if you fix an important Lie superalgebra, then simple modules were classified by say and Katz for important finite dimensional Lie superalgebras. And they are parameterized by this L, I note by Y tilde L. So simple modules are parameterized by this set, the set of functions psi, such that psi from N to C is a Lie superalgebra homomorphism. And also like, so we consider only even homomorphism. So since it's an even homomorphism, so since C is assumed to be even, it has to map odd part to 0. And we also require this property. Okay. So here's how we construct the irreducible modules for the important finite dimensional Lie superalgebra. Let's fix a psi in F, and one can choose a maximal subalgebra of the important Lie algebra N, which I denote by S. And it's a maximal subalgebra with the property that if you restrict this linear function, it's still a Lie superalgebra homomorphism. So one can choose a maximal subalgebra of N such that the restriction of psi is still a Lie superalgebra. And then, of course, and then what you do, you induce from S to N. You get this look at the induced modules. These induced modules are from S to N, they are always irreducible, but they may not be one dimension. If S is equal to N, then it will be one dimension. If the maximal subalgebra is n, then you will get one dimension. Psi will be what? One dimension. Otherwise, it won't be. There are many cases like it's not one dimension. Then the set of all irreducible modules is parameterized by y tilde L notation. I use I psi. Of course, like there is also parity change factor. With parity change factor and this I psi, they form a complete list of irreducible simple, it's irreducible modules for n. There were some, I think there were some issues with small mistakes in Katzberg, and this was fixed by here. In later papers, not big issue, but this is the complete description. The correct version of it. Okay, so you know the reason we cannot since because of this not being one-dimensional irreducible modules creates a problem to extend many results. Okay, so I will give you a definition of Whittaker module one more time. So again, if you want to define Whittaker modules for any algebra, we need a triangular decomposition. That G be a least superalgebra with a triangular decomposition, and let psi be a non-zero least superalgebra homomorphism. It means it maps odd part to zero because it's Z2 homomorphism. Again, what's a non-zero? What's a Whittaker vector? A Whittaker vector in a module B, G module B is a vector that psi x and x by psi for all x in M. And then what's a Whittaker module? It's a cyclic module generated by a Whittaker vector. Exactly the same definition. But these algebras, they have interesting triangular decompositions. They are not quite symmetric, so it creates a problem to state things for arbitrary triangular decompositions. You have to fix some kind of triangular decomposition and stick to this decomposition to get some results. Okay, so simple, again, I don't want to say this, but my talk is over the complex numbers. Everything is over the complex numbers. Simple least superalgebras, there are two types of simple least superalgebras, classical and Cartan-type. And this classification was done by Katz in 1970s in his main paper. Classical means the even part. Remember, even part was a Lie algebra, so this should be a reductive Lie algebra to be called classical. Otherwise, called Cartan. If the Lie algebra part is even part is reductive Lie algebra, it's classical. Otherwise, it's Cartan. So I will focus on these four types. I use that in my thesis. So I worked on this algebras on my thesis. In this talk, I will just focus on Cartan-type superalgebras. We have four infinite family of these algebras. Like Wn, Sn, tilde, Sn, Hm. So it's not four of them, four infinite families. And let me say this, Wn is the main one, and all three are subalgebras of it. And I will base my talk on Wn. I don't want to give definitions, all definitions, just Wn. For the rest, my talk like G will be a Cartan type. And sometimes I will focus on Wn for some results. It's Wn. Okay, what's Wn? So if you take an n-dimensional vector space, here's the definition of Wn. If you take an n-dimensional vector space, you can look at its exterior algebra. This is a superalgebra because it's Z2 graded. So you have even wedges, and then you have odd wedges. The vector space of all even wedges from the even part, odd wedges from the odd part. Then you can look at super derivation, and super derivations like Z2 graded derivations of this exterior algebra. And what is super derivations? Derivation basically you have to put the right signs when you switch things. It's same thing. Like so dxy is not just dxy plus x dy. You have to put, since you're switching x and d, you have to put the Z2 gradient part. Then Wn is what? The least superalgebra of super derivations of n-dimensional exterior algebra wedge n. And the bracket is again super commutative bracket on all cases. Yeah, of course, you have composition derivations. Right. What is nice about this algebra is that this admits a Z grading. So it's a very nice property. I don't know if the definition of it is nice, but it has a very nice property. It admits a Z grading. I think this Z grading comes from exterior algebra, wedge n. It's concentrated in degrees -1 up to n -1. So it admits a Z grading. Another thing about this nice grading is that this Z grading is consistent with Z2 grading. Like if you take the even parts in Z grading, you get even part in Z2 grading. If you take the odd parts all together, you get odd part in Z2 grading. It's a consistency grading. It makes you use like both gradings at the same time. So another nice thing is what it has many nice properties. Probably I don't know, but I look at this many times. Each time probably you look at it, you say something nice. But one of the nicest properties is the zero part. If you zero part in Z grading, not Z2 grading, this is isomorphic to Lie algebra GLN. This is mostly what people focus on to get the results about it. So you look at basically you work with GLN and you extend, you try to get something from what you have GLN to the whole algebra. Not the all even part, just the G0 part. So from now on, G0, the Wn0 is GLN, so n by n matrices. Okay, let me fix some notation. Like I said, Cartan-Lie superalgebras, they emit a Z grading starting at degree -1 all and ending up some at positive degree. And I will denote this all positive part, direct sum of all positive part by G plus. It's not quite symmetric Z grading, so you have only -1 part on the left side. Like I said, so for the Lie superalgebra case, so you have to fix certain triangular decompositions to get some results. So any important triangular decomposition people use is called distinguished triangular decomposition. The way you construct this is as follows. You take a triangular decomposition of the GLN, which is G0 part, and then you turn it into a triangular decomposition for G. Basically, what I do, I add G plus to N0 part, get the positive part, which my N will be what N0 part in G0 plus all positive parts in Z grade. And then n minus will be -1 part plus the negative part of n in G0. This is called distinguished triangular decomposition. As expected, so this is how it's circumscribed. Okay, so I will fix some notation again. We have everything. Since we have the integrated vector space, we have even simple roots, odd simple roots, even roots, odd roots, etc. We don't, for the purpose of this talk, we don't know. We don't have to. I'm not using this notation much. Okay, so what I will do is as follows. So I will look at, I'll fix a psi net, and I will look at simple roots in G0 part, which is delta 0. And we construct subalgebras of the Lie algebra GLN, which are called, I think they're called Levi subalgebras. Sometimes I'm confused about the names. It's Levi subalgebras. We construct several Levi subalgebras for each psi. So as follows, let's fix a psi in N. Then we'll say psi, and I will look at this. I will denote S psi will be subalgebra. It's a subroot of subset of simple roots of G0, such that the psi restricted to G alpha is not 0. So I'm just looking for psi goes from N to C. I will look at the roots, simple roots in delta 0, not that all even roots, such that restriction of psi is not equal to 0. This is a subset of simple roots for GLN. And then we will look at phi sub S psi. These are the roots. So phi sub S is what? Phi sub S is a free abelian group generated by S. And I will look at roots created by, phi intersected with phi, the free group generated by, free abelian group generated by phi sub S psi, Q sub S psi. Sorry, I hope I'm saying clear. All I do is like, I look at the free abelian group generated by S psi, and then I look at the roots inside this space. This is my set of roots basically. And then we have the while group. Basically, the while group is the while group of G0, which is a GLN. We have half sum of positive roots, rho, and we have dot action at the same way. Okay, and then we construct the Levi subalgebra of it. It's basically H plus alpha in this phi sub S psi, G alpha. It's a finite dimensional reductive subalgebra of G0 because the simple roots are coming from the 0 part. Okay, and like I said, if psi is non-singular, basically G S sub psi will be delta 0, all simple roots, and G psi is basically G0. So because if it's non-singular, this S is equal to all simple roots of G0. Right? And then you can use basically what you have to do after having this Levi decomposition for G psi, you can get a decomposition, Levy decomposition for G. Basically, you take what you have, you positive part is what all positive roots which are not in positive part of it by S psi. This is the positive part in the Levy decomposition for G, and then what minus part will be a negative sum of this root. G minus alpha basically. So alpha in 5 plus minus G minus. Let me say this. If you have G alpha, you may not have G minus alpha. Just 5. That's why I depicted like this. It's not symmetric. So if having a root alpha and minus alpha may not be there. Yeah. Then we have a decomposition for G. So which is R. I use the notation R psi plus and R psi minus. Okay, so first result is what? So you look at the modules for G psi. Constants prove this result for semi-simple Lie algebras. Since G psi is reductive, we have almost same result using same proof. You can show that up to isomorphism, there is a if you fix your psi up to isomorphism, there's a unique Whittaker module with central character lambda, which I'm using W psi chi lambda. He uses a different notation. And these are called standard Whittaker modules. This is basically follows his proofs, slight modifications, it's the same thing. So this is the set of all Whittaker modules for G psi. I do it by W psi lambda. Okay. So remember, W was a module for G psi, and then you can induce it up to G, make it a G module by using induction. We denote this module by M tilde. By letting positive part R psi plus act by 0. All right. And then if you look at this, a G psi module, it's isomorphic to negative part times W psi, and you can do the same thing for G0. Remember, G psi is a it's a reductive subalgebra of G0. You can decompose, you can give Levy decomposition for G, and you can make the connection between G0 and G. Then you do the modules. This is basically what's going on. And then I'm using M notation for the induced modules from G psi to G0 part, the Lie algebra part. And I'm using tilde notation for the Lie superalgebra, the highest level. Okay. There is work of Milic and Sorgen on this module. They look at such module that we follow data. Yes, we define the same thing for this basically. Of course, you can make connections between these modules. So the G module M tilde will be isomorphic to extended algebra G minus 1 times this induced module from G psi to G0. It's just it's infinite dimension, but it's basically M times a finite dimensional module, finite dimensional vector space. Of course, when psi is non-singular, so we have this. Right? So we M tilde is equal to what? Exterior algebra on G minus 1 tensor with M. M is what we call induced module for what? For G0 from G psi. Okay. Okay. One thing we should prove to talk about when we talk about description of simple modules is we show that this induced modules, Whittaker modules for G, M tilde, they admit a composition series, and composition factors are isomorphic to irreducible Whittaker G0 modules W. This is one of the things we did in our paper for the classical case, and I mean same proof for the Cartan-type, basically. So this induced modules, they are Whittaker. I forgot to say these modules are Whittaker modules. So these induced modules, they are Whittaker modules. We look at these modules only. We look at so when they are simple. So how do you get simple modules from them? Right. The composition factors are isomorphic to W's for when viewed as a G0 module. Right. Of course, this we have.
So this is like a silly question. Can you back up? So this gamma G minus 1, so that kind of identifies with like the part of the universal enveloping algebra, that Lie algebra, or Lie superalgebra on G minus 1. Is that right?
Yes, that's right.
And that's one.
This is a set of the roots of that part.
Yeah.
Yes.
And so when you do stuff, that's kind of the part that's left over.
Yes,
Okay.
yes. This is, I think this is where news are coming, new, the notation, plus notation, because it's
Yeah.
tensor.
Yeah. Yes.
Phi is set of weights of where G minus. It's coming from there. Okay, basically, I'm saying for this one, I'm saying that, so this induced Whittaker models and tilde, which we look at, they admit a composition series, composition factors are irreducible. They're isomorphic to like standard Whittaker models. No? Okay, and then of course, like we look at when these models are simple, we looked at this in classical case, in the Cartan case. So it's simple, basically. So this is like following Cartan's results. So this induced module and tilde will be simple if it contains a unique cyclic Whittaker vector. So this is not hard to prove, say both those. And then you can use that action to make connection between these modules. And one other thing we showed, like, which is important, this module has a unique maximal sum module and unique irreducible quotient. And we denote this quotient by L tilde upside down. Tilde does not go, they go with N tilde. Right? And if you look at M, if you look at the G0 part, remember we have Whittaker modules for G0, which we denote that by M psi lambda. If this module is not simple, if we induce it up, then it doesn't stay simple to G. Yeah. So, okay. All right, so now we are trying to, like, remember I was saying, like, we want to know when these induced modules are simple, when they are not. There is some work of Vera Serganova on Z-graded representations of Cartan-type Lie superalgebras. She looks at any kind of representation, infinite dimensional, finite dimensional, Z-graded representations for Cartan-type Lie superalgebras. Okay, so she gives a combinatorial definition for irreducible modules. So according to her definition, there are two types of simple modules, typical or atypical. There are two Borel subalgebras. You can use, like, if you take a Borel subalgebra of G0, which we denote by B sub 0, you can look at B0 plus G plus. This is called maximal Borel for us. And then you have what B bin, which is you just use G minus 1 part and B0. You can construct simple models by using any of these algebras. Right? So if I use, let's say lambda is let's look at LB max and lambda. So I'll have a simple model that isolate lambda using this maximal Borel subalgebra. If let's say this is isomorphic to what some lambda prime for the minimal parabolic subalgebra, Borel subalgebra. And according to her definition, lambda prime can be written as lambda plus alpha for some alpha is in the roots of G minus 1 part, then she calls this to be like typical. Such weights, lambda is called typical if you can express if the equation one holds, basically. Okay, otherwise it's called atypical. So there are two different types of simple modules, typical and atypical. If this equation holds, it's called typical, otherwise it's called atypical. By using her results, she proves that if the lambda is typical, then the induced module will be irreducible. She proves this for Z-graded representation, but slight modification, you can show the same odds for Whittaker modules. You can show that if lambda is typical, then this induced module is simple. Her proof doesn't use any kind of Z-grading or something. It uses some kind of short, not quite short exact sequence, and uses some sequences, and it gives you this result. Right. Okay, so for any Cartan-type Lie superalgebra, if the weight is typical, then the induced module will stay simple. So if it's atypical, there are, again, she has some results. So I will just look at Wn. So if you look at Wn, lambda be atypical, and the set of typical weights is determined in her paper. So she determines this, and the multiplicity of irreducible models, irreducible Whittaker models. In this induced Whittaker models are given by this numbers, basically. Basically, the result says that. So this, if it's not simple, if it's atypical, it's isomorphic to a direct sum of two simple models. That's the result. That's what it says. You can see there are two cases in each case, most of the time. Again, so I don't think you need Z grading in her results. So it really holds here too, with slight changes. Okay, let me give, in our first paper with Emily and Dina, we were having an example. I looked at this example one more time. We were missing something there, I think something small. So we showed like as for SL2 all the induced models stay simple, but we are missing the point like lambda has to be typical to stay simple. If it's not typical, then it doesn't stay simple. It's not a mistake, but one part is missing there. So to look at this, I look at W2, since I'm doing Cartan-type algebra, so I just look at small scale, which is W2. And psi non-singular, so I looked at typical and atypical case. If you look at W2, we have three types of atypical weights. And this is how the induced model decomposes. So it's not simple, basically. It's a direct sum of two simple models in all three cases. This is for W2. And if lambda is typical, you do like basic linear algebra using like invariant subspace. You show that if the highest M tilde of psi lambda is always what it's always simple. Simple linear algebra. It's not bad. It's zero long. So you have to look at these brackets and action and all this. You show that the only invariant subspace for M tilde under the action of GR0 of the exam, basically. You fix a set of basically you take a Whittaker module, you look at that, you fix a basis, and you show there are no invariant subspace for any fixed base. I just skip this because it's a little long. I wrote this by using the notation of the use for Cartan-type algebras. Well, it's very similar to SL2 case where we use the matrix, but it's on the same thing. It stays. So basically, if lambda is typical, the induced model is always simple. But I mean, other cases, they are big, it's hard to show. Like just W2 is small, you can look at. Here I'm using the work of McDowell. He has some nice commutation relation to get how to show there are no invariant subspaces. He does it for SL2 basically. GL2, SL2, same idea. So, without his results, probably I could have had some issues to be able to explain why it's irreducible. It's not solid results on identities in SL2. There's an SL2, like a GL2 in W2.
We take one where it's not irreducible.
Yes.
Are the other composition factors that occur also kind of the storm? These modules, or are they actually different?
Composition factor, yes, they are all Whittaker models. Yes, they are all standard Whittaker models. Yes, all of them. Okay, so here is the main result. We did. So I have this for type 1, and this is Cartan type. Basically, I think psi should be non-singular here. So then if you look at so the space L tilde of psi lambda, if you fix your psi, then so L tilde of psi lambda, where lambda is A in H, so represents the isomorphic class of all the irreducible Whittaker G modules of type psi with central character lambda. Okay. Let me just briefly talk about the proof of it. The proof is very standard because we set up what in G2 we need to have to give the proof. We know this induced modules they admit, but they admit composition series where composition factors are isomorphic to standard Whittaker modules and some other results. When using homological algebra, the rest should be fine. Right? So if you take an irreducible Whittaker G module of type psi, and here G is a Cartan-type algebra. So it's generated by a Whittaker vector. So it's U of GW for some W, where W is a Whittaker vector. Right? So since V is a Whittaker G module, so it's a Whittaker G0 module by restriction. Okay, then you can look at the UG0W. Okay. And this module, this V will contain this what? UG0W. That's a G0 what? G0 submodule, right? So because V is a G0 module, right? This is a submodule of it, so it's inside, so it's a submodule. Since L is irreducible because it's generated by cyclic vector, so the L I'm taking, so it's isomorphic to one of the standards, the Whittaker modules, W upside down. It's irreducible because it's generated by cyclic vector W, just zero. It's a Whittaker vector, Whittaker module for for the algebra part. So we know Whittaker modules are standard Whittaker modules, which is W psi lambda for some number. And then if you look at the hump space of the hump space between G modules and tilde and V, this is using like homologic algebra. We know this, you can restrict M tilde to G0. If you restrict M tilde to G0, then you get M. So this is the induced part. And then in the second part, M V will be as a G0 module by restriction. I'm not writing this. Okay, so this is non-zero. This is non-zero. Okay. So M tilde we know it is a composition with composition factor isomorphic to standard modules. That's why we have like V is a composition factor for the induced module M tilde. Okay. So we know what every simple module V is a composition factor of what this induced module. The next we have to show that what every composition factor is of this one, of the form we have in our list. So understand this is very standard. Okay, so next we show that every composition factor of this induced Whittaker module is isomorphic to what some L tilde. That I'm using same notation that V be a composition factor for this module. One fact we prove like following the customs group, I mean like this center of G psi will act semi-simply on this induced module, M tilde. This is one of his main results. And if you look at this decomposition, the highest weight, which is M tilde lambda bar, we denoted by M tilde lambda bar, is isomorphic to one of these standard modules, the G psi module. This highest weight space in this decomposition is about G psi module. And it's simple. Again, following his ideas, you can put this for M tilde easily. That's what we show. Okay, and this gives us basically what we want. Then if you look at the hump space between M tilde upside lambda and V, I think it's better to like this is so if you restrict the M tilde to what, to G psi, or you can restrict to P part like G psi plus what, the positive part. So this is like P psi was G psi plus the positive part. I'm applying the same property. Then this standard Whittaker module is also a P psi module. So, and so this space should be what, non-zero, because we know what. So it's non-zero because the high space is isomorphic to what, of psi lambda. Therefore, V has to be isomorphic to what is L tilde psi lambda. Okay, do I have time? Okay, I finished. Sorry, did I finish earlier? I didn't check the time. No.
So this kind of goes back to Nate's question a little bit. So do you have a notion of projected modules in Java?
We didn't look at it, to be honest. I don't think it's defined.
Okay.
No.
Right.
As far as I know, for the superalgebra case. No.
So basically the idea is you want to be able to construct certain types of simple modules. And the Whittaker construction actually gives you a weight. So,
Okay.
but, I mean, is that the idea of this, the program kind?
Okay. I don't think we just look at simple models and using the ideas of custom basic. No more of this. I have no idea. Probably not. They are infinite dimensional models. So, maybe. I don't know much about it, but I know they are using number theory in Whittaker equations. I don't know what kind of geometry these equations has. They might have some geometry. I never checked it. So, is this what you're asking? In the cohomology, I mean, they are infinite dimensional. I don't think there's cohomology of this model is known or anything. Probably it's very hard.
Austin's paper has some stuff that we find. I forget there were some various things about special functions. What do you guys?
There is so much, and it's hard to understand. It's a heavy paper.
Yeah, I remember glancing at it. Agreed. So funny.
It's a very good paper if you can understand much.
But you know, so well. I think my advisor, who was a student at Constant, once made this remark that you don't need to know anything to read Constant paper to be really smart. He was really smart. So
It's a very good paper. So I know some parts really well because of what I'm doing, but there are certain parts I don't have good understanding. Still have questions in my mind. But the pieces I'm using here, I finally have some better understanding. It's a very long paper, 100 pages, I guess. It's a very good paper. He has many, this is just one small, like Whittaker Modules, a small part of it. Classification of simple.
I remember looking at it years ago, and I remember there being a lot to it, but I don't remember.
It's a good paper and it's very heavy. And people use these ideas for Whittaker model thing, or if you look at all papers after this, when the algebra structure, they use these ideas, I would say. So, all the algebras which have a triangular composition, they use similar ideas. And main idea is, I think, is an idea.
And the bell was the student.
Was he? Okay.
My advice.
Your advisor? Okay. He has some 2 applied papers, very nice. He explicitly looks at SL2 on SL2. He helped us to look at, he looks at the algebra case, SL3 and SL2. We did SL2 by using some of his observations and commutation relations.
Questions? Let's speak again.
Okay.